Alrighty, welcome to the next unit, Unit 7. This is going to be on systems of equations and inequalities. So here we're going to learn not just about graphing one line at a time, but what happens if you have more than one equation in the same problem. How can you use that either mathematically or for real-world examples to find the solution to a more complex problem. So there's going to be multiple different videos, and we'll start off with the first one. An introduction, what is a system of equations, and what are some simple ways to get an idea about the solution. So let's review briefly. When you had a single equation, that was just some kind of relationship between variables. Typically we had just two variables, x and y. So we used x as the input and y as the output. So the solution for a single equation was some set of values that made the equation true. So if you had a linear equation, the solution would be a point that was on that line. So for example, if your equation was 3x plus y equals 5, then the point 1, 2 would work, because if you plug in a 1 here and a 2 here, 3 times 1 plus 2 is 5. Or 2, negative 1 works. So there would be an infinite number of solutions because there's an infinite number of points which lie on that line described by this equation. So that was a single equation. So now for a system of equations, what you have is you have multiple equations. Most of the systems that we'll be dealing with will just have two equations, but you could have a system of equations with more than that. And they'll involve the same variables. So you might have two different equations, both dealing with x and y. And to get a solution to the entire system of equations, we'll abbreviate that SOE. To get a solution to the entire system, you have to find a point, or more than one point if you're depending on what kind of system you have, but you have to find a point that makes all of the equations true. So it has to be a solution to every single equation in your system in order to be a solution to the system. It has to be a solution to each of the equations within your system. Alright, so one of the easiest ways is to solve by graphing. To be a solution to an individual equation, it just has to lie on that line. So if two lines cross, then every point on one line, here, let me just go like this. Every point on this line is a solution to this equation, and every point on this line is a solution to this equation. So this point right here in the middle, it lies on both lines, so therefore it's a solution to both equations, and therefore it's a solution to the system of equations. So the single point where the two lines cross is going to be your answer or your solution to a system of equations. So if you want to solve by graphing, you can graph both equations on the same axis, so you'll graph two of them next to each other or on top of each other, and they'll cross at the solution point. Okay? So when you're graphing these, there's going to be three possibilities. The simplest case is they cross and you find one solution. So they could cross like this, they could cross like this, they could cross like this. So anything like this, they'll cross and you'll have one solution right here, or right here, or right here, wherever it is. But there are some other possibilities. What if the lines don't cross? So one of the possibilities is the two lines are parallel, and so they never cross. So when you're what happens then is, in the act of solving a problem, you'll come to a statement that's always false. Because if you're trying to find out where two lines cross and they don't cross, you'll never find a solution. So if the two lines are parallel, that means they have the same slope, but a different y-intercept, and your solution will come out to be false because there is no solution. So here you'll write no solution. Here there's one solution. And then the other option is the two lines are actually on top of each other. This means that both equations are really describing the same line, but they're just written in a different format. So one could be like this. Y equals x plus 1, and 2y equals 2x plus 2. I hope you can see that if you double the first equation, you get the second equation, but it's really the same relationship between the variables. So here, if you were to graph these two, they would be literally right on top of each other. And so if you want to ask yourself, what is all the points that works in the first line and the second line? Well, every single point that's in the first line is also on the second line, so every single point is a solution. So then you have all points are solutions. So you could have no solution, all points as your solution, or just one point as your solution, depending on the possibilities. Okay. Another possibility is that you could solve these using a table. So if you have two equations like y equals x plus 1 and y equals 2x minus 3, you could make a t-table, and you could put x here. Let's call this y1 and y2 for equation 1. And let's try plugging in some numbers. So if we plug in 0 in the first equation, we get 1, because 0 plus 1. In the second equation, we get negative 3. Then we plug in a 1 for the input. Output we'll get here a 2, and the output we'll get here is -1. Then we plug in a 2. Output here we get is a 3. The output here we get is 2 times 2 is 4 minus 3 is 1. Then we'll plug in a 3, and we get a 4 here. Oh, sorry, I'm getting a little off. 3, 4. If we plug in a 3 here, we get 6 minus 3, which is 3. And if we plug in this one, a 4, we get out a 5. And if we plug in a 4 here, that's 8 minus 3, which is 5. And what you can see here is you can compare the output of the first one and the output of the second one. So if we were to take a look at the graph of these, when they both have the same input value, you're looking at the same vertical kind of line. This one has an output of 1, this one has an output of -3, so they do not match up. They don't have the same output value. They're not the same point. But when we get down to here, if you input a 4 into either equation, you get a 5 out. So that means the solution to the first equation is 4, 5, and a solution to the second equation is also 4, 5. So we found a single point, 4, 5, that works in both equations, and that's therefore the solution to the system because it's a solution to both of them. So it's one point that works in both places. Okay, let me do one more example of solving by graphing, and then we'll be finished with this brief introduction to kind of get you an idea of what a solution to a system is. So say we have, let's just do this exact same one. So let's graph this one. If we were to graph this line, y equals x plus 1, the slope is 1 and the intercept is 1. So we go, the slope is 1, intercept is 1, so we start at 1, we go over 1, up 1, over 1, up 1, over 1, up 1, over 1, up 1, like that. We graph this line in here. And then this one has the intercept of -3, so we start here. We go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. That's the point where we cross, so I'll make it nice and big. Up 2 over 1. And so if we graph this line in here, sorry, I haven't drawn it all that well. It's difficult with the mouse. But you get the point, I hope, and that is that the point where they cross on the graph is exactly the same as the point you'll find by the table, which is a point that works in both equations. So to be a solution to a system, you have to work in all the equations within that system, and the very easy visual way to find these is by making a graph and then looking where they cross. So you might be wondering, well, what if they don't cross at a nice whole number where it's easy to see? Is there any other way to do this? And in the future videos or lessons in class, we'll look at exact algebraic ways to solve for the place where these two lines cross and get values that you may not be able to see clearly on a graph.